Okay, hello everybody and welcome back. We're moving on to my favorite chapter of the book. In many ways, one of the chapters that we've been working toward for a very long time. It's a culmination of a lot of the things we've been working on this whole semester. You're going to use pieces of linear ODEs, your linear algebra, complex analysis, numerical methods, etc. Because, we're getting to the point where mathematicians, even mathematicians like me, really don't have a really efficient tool for handling these problems. And so you're going to see that things are a little bit piecemeal. And that's because we're getting to this chapter that you've probably heard about called chaos, right? Chaos theory, butterfly effect, etc. All of those ideas are really tricky to deal with. Okay, there's kind of two sides to this coin, though. The other side is called stability, and we'll tackle that first. We're going to tackle that today. But I do want to mention that today we're working, and actually for this whole chapter, except for some examples where the non-autonomous systems get a little bit easier for examples, we're going to be considering autonomous ODEs, and that's because if you're talking about if a system is stable or chaotic or something like that, you want to use the fact that the system, we're going to say if stable, then always stable. If chaotic, then always chaotic. So just in the sense that, I spelled that wrong. Just in the sense that, if we define a stable system, we want to define it for all of times. Otherwise, you're saying, oh, the system's stable, but 2 seconds later, it just completely changes its behavior. So that's why we're going to work with autonomous systems. For somewhat straightforward reasons, you could argue that this is, you can still apply these techniques to non-autonomous systems and then just apply them at each instant in time and see how it behaves. But that just gets so complicated that we avoid it for now. I have this remark in section 0, I guess, which is where I'm introducing these languages of ODEs versus dynamics versus dynamical systems, because actually this subdiscipline of math called dynamics is related. It's heavily related to ODEs. It's not exactly the same as ODEs, though. So you'll hear people say that they study dynamics or they study dynamical systems, and there's actually two approaches to these. So anytime somebody will talk to you about dynamics or dynamical systems, there's kind of two notions of these dynamics, but both of them deal with IVP. So it's an initial value problem of some sort, but if I look at my first situation here, this is a discrete time setting. So this is a discrete time dynamics. And the idea here is that you just let the next step, it's like you make a chain, and each step in the chain depends on the previous one underneath some function, right? But we're moving forward in discrete chunks in a discrete time dynamics. And then an ODE IVP. Right, an ODE IVP, this is what we're going to be studying. These are continuous time dynamics because you don't have steps where you get pushed forward. You just kind of follow some path where every point in the path cares about its infinitesimal past. So those are the two sets of dynamics that dynamicists or people who study dynamical systems are going to care about. But we're only going to be studying on the second because the second is also a subset of ODEs, right? So in the Venn diagram sort of sense, there's a huge overlap between ODEs and dynamics, and we're just going to be studying the ODE's half of dynamics. And in fact, if this operator n happened to be actually partial differential operator, you could actually refer to this as a PDE that has some initial value. So, dynamicists can also study PDEs. Differential equations people study dynamics all the time and vice versa. It's just that there's the whole discrete time dynamics, which is a little bit different. You can also push yourselves into very pure areas of dynamics, like the Collatz conjecture, for example. That's a dynamics question that has nothing to do with differential equations, unless you take some very strange perspectives at it. Anyway, a dynamical system is just the collection of equations which produces a dynamics. So the solution to these is called the dynamics. A dynamical system is the equations themselves. Anyway, so that's the difference between those three, and kind of, I guess, the same thing about all three as well. Moving on to actually section 13.1, which is titled Equilibrium Points, Stability, and the Hartman Grobman Theorem. And the whole point of this entire chapter is to basically ask the question, chaotic systems, nonlinear systems are really hard to solve. They're really hard to predict. What can we actually say about them? What's the minimum, what's the maximum amount of knowledge that we can say about them? In the sense that there should still be some qualities that we can show are true about the solutions to these equations, even if we can't solve them. That's where we're headed. And a very classical question to ask is, can we understand the long term or infinite time? This is how we're going to understand it mathematically, but non-mathematically, you would think long term behavior of a system, even if we can't predict it in finite time. So, for example, if I'm going to mix Kool-Aid into water, I can't predict where any individual sugar molecule will end up. And I think everybody agrees with me that I'm not going to be able to predict where any individual sugar molecule will end up. But I do know something about the system. I know that the system will equilibrate to an actual drink, right? It won't be, the sugar won't all of a sudden, I mean, assuming that you've done a good job mixing it, it won't all settle into one spot. It's going to mix evenly, and you're going to have some sort of long-term behavior of that Kool-Aid. And that's something that we can say with certainty about it, even if we can't predict some individual behaviors. Some terms that you'll see mathematicians use to refer to some of this is either asymptotics or stability analysis. Asymptotics can go in other directions as well. You could be caring about things that aren't time and still trying to take them to infinity. But one of the infinities you can encounter is a temporal infinity, and that'll be a subset of asymptotics. Stability analysis, that's basically what we're thinking of here. And what we want to start with is this idea of an equilibrium point, right? Because thinking about the Kool-Aid, understandably Kool-Aid, there's no point that reaches equilibrium, but we can think of some other systems where there's truly a single point, which is in some sense the long-term behavior point. So an equilibrium point by definition is any point y star, and we're letting it be in the complex numbers, I guess. You could just let that be the real numbers too if you want. So it's any point y star for which the right-hand side of our autonomous IVP equals 0, right? Because if the right-hand side equals 0, then that means the derivative, also known as the change in position, is 0 over time. And what would it mean to be in equilibrium? Well, it means that the change in position is 0 over time. So that's why we call it an equilibrium point. So really what you're looking for is roots. If this is some sort of equation, or not an equation by itself, but if that's an expression, you set it equal to 0, you're looking for the roots of that expression. That's how you find equilibrium points. We also call it a fixed point, because it's a fixed point to the dynamics, in the sense that if you start somewhere, you're fixed at that point. And we have a really nice example of this. Let's picture a bowl, and let's picture dropping an orange into that bowl. The orange will either fall directly at the center, and it'll rest in the center if it falls there, or it's going to fall into the side of the bowl, and it'll roll to the center. But in either case, the ball will equilibrate to the center of the bowl, which in this case, the center would be our equilibrium point. And that's a completely heuristic argument. Let's actually look at the math which describes this. And we can describe this mathematically using gradient descent, which means I'm going to start with a potential function which describes the shape of the bowl. Which in this case, I'm assuming it's parabolic. Okay, so my potential function looks something like this. So that's a perfectly valid potential function. If you recall your Calc 3, that's a paraboloid. And you calculate the gradient of that potential function, and then you let yourself evolve in the negative gradient direction. And if we go ahead and calculate the gradient of this paraboloid, we get just x1, x2, and then the negative gradient would be, technically I've added a matrix there, but the negative gradient would just be negative x1, negative x2. And so I've represented that as a linear operation on the vector x1, x2. And so I have this matrix negative 1, 0, 0, 1 acting on x1, x2, and that's a dynamics that we can perfectly predict the future of because it's linear. Right? You should all be able to view that as linear. And we see that no matter where we start, right? So if I initialize at some point x1, 0 and x2, 0, no matter where I start, the long time behavior is exponential decay. And it's exponential decay to the point 0, 0, right? So the infinite time behavior of this system is to head to the point 0, 0, which is our origin. So we can show that both mathematically as well as heuristically, where everybody agrees that 0, 0, the bottom of the paraboloid will be where we end up in infinite time. So then I want to caution everybody, because the wording is interesting, because you would almost think that if an equilibrium point exists, then the solution has to end up there after an infinite amount of time. And that's not true. So this is not true. Equilibrium points can exist, and they don't necessarily attract everything. They could repel things. They could be completely indifferent towards attraction or repulsion. All that we need for an equilibrium point is that if we start there, we stay there. It's like balancing, right? You can either balance, you can balance a pencil on its side, you can balance a pencil on its tip. If you balance a pencil on its side, it's not moving. If you balance it on its tip and you're really good at balancing, it's also not moving. Both of those are equilibriums. One is going to be the long time behavior of a system, most systems, right? And the other one's not going to be the long time behavior of most systems. So we'll look at this next example, which is an orange dropped in an upside down bowl, right? So if we flip our bowl upside down, we drop an orange on top of that. If it lands in the center, it stays in the center. Nobody's going to disagree that if I perfectly drop that orange right in the center of the bowl, I'm stuck there. But if I drop it anywhere away from the center and the bowl is upside down, it's going to roll off the edge, right? So the center is still technically in equilibrium, but if I drop it anywhere except for the equilibrium, then I actually fall away from the equilibrium. And we can compute the math here as well. All we have to do to our potential function is flip it upside down. So now I'm looking at a paraboloid that's pointing downwards. It starts at 1 here, and now my paraboloid points like this. And you can very quickly imagine if I drop an orange on this, there's my orange, I drop it, it's just going to roll off the side. Unless I start at the point 0, 0. If I start at the point 0, 0, then I stay at 0, 0. But if I drop it anywhere else and I compute the infinite time behavior, then the infinite time behavior of the x1 direction is plus or minus infinity. The infinite time behavior of x2 direction is plus or minus infinity. We're assuming our bowl is infinitely large. But either way, you get the idea that mathematically we can compute this, and we get the negative of the matrix we got before, which makes perfect sense. And we're just going to roll off. We're going to roll off to plus or minus infinity, even though an equilibrium point exists, right? So just caution, equilibrium at 0, 0 still exists. It's just not stable. Okay, so this is one of these close only counts in horseshoes and hand grenades situations. And so we have to answer this question. This is the whole point of this section, is what determines the behavior of initial conditions near equilibrium points? Is there a way to classify which equilibria attract their neighbors and which equilibria repel their neighbors? Is there an easy way for me to tell right away, looking at the math, only the math, not the actual bowl? Because if I'm looking at the bowl, then it's really easy to tell how the behavior exists. But suppose I have a 45,000 dimensional bowl. Is there an easy way to predict where the equilibrium are attracting or repelling? Okay, so we use these languages of stable or unstable to reflect the equilibria, and now we're going to define them. A stable equilibrium is an equilibrium for which if I start near, okay, so maybe I should describe what's happening here. It's an equilibrium point for which if I start my dynamics in that set, so that's a set, and in particular the set, this is the set of all y0 initial points within a distance, and that's radial, right? It's a radial distance of r away from my equilibrium point y star. So a stable equilibrium point is if there's a small enough r, if I start close enough to this equilibrium point, then I stay near the equilibrium point. So that's what this is saying the distance never exceeds what I started at if I started in a small enough region around my equilibrium point. So here I wrote that in quotes. Heuristically, it's saying if it always starts near the equilibrium point, then it always stays near the equilibrium point. That's what it means to be stable. To be unstable is just if it does not satisfy this property, then it's unstable. So let's look at a nice example here. We're going to start with a nonlinear dynamics now, finally. I mean, we could jump back to the orange. It's somewhat clear that everybody agrees that the orange, when the bowl is facing upwards, regular bowl style, the 0, 0 is a stable equilibrium, because if I drop the orange near the bottom of the bowl, I stay there. And if the bowl is upside down, that's an unstable equilibrium, because even if I drop the ball near the equilibrium point, I eventually leave. I fall away from it. But let's look at a nonlinear dynamics, and this is just in one dimension. So it's y prime equals y times 1 minus y. And you can go ahead and use your separability. So that's what that theorem is. It's just this is a separable problem. You can solve it perfectly. And we get the following. We get that the dynamics is wherever I start times an exponential divided by 1 plus wherever I start exponential minus 1. Okay? So that's the dynamics that we're going to have here. And it shouldn't be too hard to figure out what are the equilibrium points. All you do is solve that equation equal to 0, and we can see pretty quick either y is equal to 0 or y is equal to 1. So these are the equilibrium points, 0 and 1. And we want to check if they're stable or unstable. And an easy way to do this is just like I said, we're going to solve the dynamics and ask ourselves some questions about these points. And so let's say I start near the equilibrium point 0. which I'll represent mathematically as saying 0 plus epsilon, where I imagine epsilon is a very small number. And I look at the output of the dynamics then, or I look at the trajectory, and I'm just going to compute that with a limit as t goes to infinity. But it's clear on this trajectory, no matter if epsilon's positive or negative, what I get in the infinite time limit is really, epsilon e to the infinity, epsilon e to the infinity. These dominate the one and the plus or minus epsilon that I would get there. So I really have epsilon e to infinity over epsilon e to infinity, and my limit will be 1. Now 1 is not close to 0 in infinitesimal terms, right? So that means I've left, since this is not 0, or I should say not close to 0, I've left the region near 0, hence this is unstable. That's the definition of unstable, is if I compute my infinite time and I eventually leave the region near the point, then I'm unstable. And that's only true for positive epsilon. Actually, for negative epsilon, there's a finite time at which I actually reach minus infinity, which also leaves a neighborhood of 0. It's minus infinity is no longer near 0. So in either case, I'm unstable. But if I instead decide to let myself start near 1, my other equilibrium point, and I can represent this mathematically as 1 plus or minus epsilon, I'm going to place my initial conditions there and calculate the trajectory at time infinity. And it's really easy to calculate this out. I'm just getting 1 plus epsilon e to the t, 1 plus epsilon e to the t, other terms dominate, and I get 1, right? So my infinite time behavior there is 1, which ideally you all agree with me that 1 is near 1, right? The number 1 is near the number 1. And so this is actually a stable equilibrium. We can represent this graphically as well. So I'm going to plot some trajectories here. Those are the trajectories initialized, right? So I'm initializing on the left-hand side here, 0, 0.25, 0.5, 0.75, 1, 1.25, and 1.5. Those all tend to that asymptote, which is y equals 1. And if I start below 0, then these actually all diverge and they push away from 0. But you'll notice my 0 path here is truly an equilibrium because the 0 path does not actually change, right? So 0 by itself is an equilibrium. It just doesn't happen to be an attracting equilibrium, or a stable equilibrium, I should say. But let's actually, because I did just say stable and attracting, let's take a step back and be careful, because we want to say that stable and attracting are not the same thing. So a stable equilibrium, you'll recall, means if I start near the equilibrium, I stay near the equilibrium. That's all it means to be stable. It does not say that I approach that equilibrium. It just says I stay near it. And what we get out of this is that, what I'm trying to say is that orbits of equilibria are stable. Okay, so if I'm orbiting an equilibria, I can do that and remain stable. I don't need to get attracted to the equilibrium to be classified as stable. So if we look at one of these, this is Hamiltonian dynamics in 2 dimensions. You could represent this as x1, x2, x2, negative x1 if you want. I'm using an x and a v to describe x as the position of a particle, v is the velocity of a particle, hence v prime would be acceleration, and x prime is the velocity. And this is the classical Hamiltonian system. You can make it a little bit more complicated than this in higher dimensions or different potential functions, but we're just working with a parabolic potential here as well. And the Hamiltonian system solutions, now these are parametric plots. Parametric plot, meaning this is my x-axis, this is my v-axis, and time occurs in this direction. It might be the clockwise version of that, but I think that's right. Yeah, that's right. So time occurs in this direction. So it's like over time we're orbiting, parametrically shown here. So I'm orbiting the point 0, 0, which is very clear as an equilibrium here, because if I just have both x and v be 0 right away, then the right-hand side is 0. And so I'm always orbiting 0, 0, and certainly if I start in a tiny region around 0, I'm never going to leave that tiny region. So that's what it means to be stable in maybe this parametric plot setting. And so we see orbits are stable without necessarily being attracted, right? None of these orbits are tending toward the middle. So that's just something to keep in mind. We will now define attracting or repelling, because this is something slightly stronger than stable, right? So these are stronger than stable or unstable. They require something extra to be able to enforce that we're actually tending to a point. So a point's called attracting if it has the same property of stability, but actually it has the extra property that the limit does tend to the equilibrium point. Okay, so same as this part. This is the same as stable. Same as stable, but tends toward equilibrium. Okay, so that's what I have here. If the limit actually reaches equilibrium in infinite time, then I'm called attracting. And repelling is a little bit trickier than just saying it's not attracting, because orbits, right? Orbits here are neither attracting nor repelling. They're stable, and yet they don't attract nor do they repel. Repelling is a little bit tricky. We say it's repelling if it's an attracting equilibrium. So it has to be attracting in time reversed dynamics. Okay, so it shouldn't take you too long to convince yourself that the time reversed dynamics is just placing a negative sign on the right hand side. So in time reversed dynamics, you just put a negative sign on the right hand side, and then you ask yourself, am I attracting in the negative dynamics or the negative time dynamics? And if the answer is yes, then I call myself repelling in the time forwards dynamics. So if I jump all the way back to this earlier problem where I had my 0 and my 1, 0 here is actually a repelling equilibrium point, because suppose time moved here. So if we let ourselves go in reverse time or negative time, then actually you can see that all of the dynamics are converging to 0. And so I have a repelling equilibrium at 0. And then the forward time, use red to describe forward time. In forward time, 1 is an attracting equilibrium, and so 1 is attracting here. So that's what it means to be attracting or repelling, as opposed to just stable. It's a stronger condition than stable or unstable. Everything which is repelling is unstable. Not everything which is stable is attracting or repelling. Not everything, and then everything which is attracting is stable. I mean, you'd be able to convince yourself of these if you just thought about it for a few seconds. And now we're finally here at the primary theorem of this section. So we went through a lot of work to get to this theorem, which is the important theorem of this section, and this is called Hartman Grobman. Which Hartman Grobman is a theorem which immediately tells us if an equilibrium point is attracting or repelling. Or I should say, gives sufficient conditions on whether an equilibrium is attracting or repelling. And in fact, it's the corollary that does this. So maybe I'll add that in here. We'll see the corollary in a bit. Corollary. So the corollary is going to give us some sufficient conditions on whether or not an equilibrium is attracting or repelling. And it's actually really easy to calculate these sufficient conditions. And that's why this is a fantastic theorem. So what does the theorem actually say? The theorem says, suppose I have my autonomous dynamics, and suppose I have an equilibrium point, which means the right-hand side is equal to 0, right? What it says is if the real part of the spectrum of the linearization, not quite the linearization, of the derivative of n at y0 or at y star is non-zero. Okay, so I'm gonna specify this. The real part of the eigenvalues of the derivative of n at y naught or at y star are non-zero. So we need that to be true. This is why linearization is important. Then there exists a map, var phi, it's a variant on phi. So phi sub y star, so the map depends on y star. And this map has a few properties. It's continuous, it's invertible, and it maps y star to 0. It should be y vector star to 0. And what we get out of this is that if we solve the linear dynamics, here's a linearized dynamics. So if I solve a linearized dynamics, because this d sub y star n, that's a perfectly linear operator. It's like the linearization. If I solve that linear dynamics and I just modify my initial condition by whatever this phi is, then I can actually recover the original dynamics using the following. So I'll say, what is this actually saying? This is saying, given these modified linear dynamics, I can perfectly recover the true dynamics with this formula. So I solve the linear dynamics, right here, this is the solution to the linear dynamics. I solve the linear dynamics, which have been modified by phi, right? So that the initial condition has been modified by phi in the linear dynamics. But then all I have to do is compute phi inverse on that linear dynamics, and then I recover the regular dynamics. And that's extremely powerful, right? Because it's telling us that I do not need to solve a nonlinear dynamics. And we all know how hard nonlinear dynamics is to solve. All I need to do is solve a modified linear dynamics and then compute the inverse of phi. And in fact, the Hartman Grobman theorem tells you what phi is. It's not the easiest thing to calculate, but it's a lot easier to calculate than the nonlinear dynamics in the first place. But I do want to mention something. This is only true in a small enough region around the equilibrium point. So I'll say, but it's only true in a small enough region around the equilibrium point. So you have to make sure that you're starting somewhere relatively close to the equilibrium. The conditions for that closeness are also included in the true statement on the theorem. So long as you start close enough, then you can solve the system this way. And we will not be proving it here. This book is Teschel's book, which I did include in the supplementary text. So this is Teschel's ODEs and Dynamics. So that's the book that has a proof of this in it. And in fact, the corollary is what we care about, because the corollary says something very, very special. It says, so the Hartman Grobman theorem said that if the real part of the spectrum was non-zero, then the theorem holds. The corollary says if the real part is strictly negative, Y star is attracting. If the real part is strictly positive, Y star is repelling. So there's just two conditions in the corollary. It just says, is the real part of spectrum of linearization negative? If the answer is yes, Y star is attracting. Is the real part positive? If the answer is yes, Y star is repelling. And so this is just a fantastic theorem. All you have to do, hence, all we need to do to classify equilibria is calculate the spectrum of the linearization at the equilibrium, right, at Y star. So that's what Hartman Grobman tells us. And if I scroll down, we can look at this problem again and ask ourselves to calculate the stability of the equilibrium points here. Now, we already did this. We already found out that 1 was stable and 0 was, I guess 1 was attracting and 0 was repelling. But we can do this using Hartman Grobman now, because we just calculate our linearization, which in one dimension, what is the derivative? It's just the partial derivative in y. So I'm going to compute a partial derivative in y of y times 1 minus y, and I get 1 minus 2y. And if I evaluate that at the equilibrium point 0, I get 1, which is, for a 1 by 1 matrix, the value of the matrix is equal to the spectrum. So spectrum 1 equals 1, which is positive, and hence repelling. And I do the same thing at the equilibrium point 1, and I get negative 1. So the spectrum of negative 1 is negative 1. This should be a set, I guess, which is negative, hence attracting. And so you can see how quickly Hartman Grobman just gives us the answers on the equilibrium points. All we need to do is calculate a derivative and calculate a spectrum. And if I want to repeat this with maybe a higher dimensional system, I can say find and classify the equilibrium points of the following nonlinear system, which is given here. And it's pretty easy. All I have to do is figure out where the right-hand side is equal to 0. And I can factor both items. And we see that this is satisfied, that both are equal to 0. Right, so I need both 0 at same time. This only occurs under technically two conditions, right? So the first condition is that these terms are equal to 0, which would be y1 equals y2. The second condition is that it's the point 0, 0, but that happens to still be on the line y1 equals y2. So those are our equilibrium points, is the line y1 equals y2. And we can calculate the derivative of this vector field, which is the right-hand side, which is just the Jacobian. And if I evaluate the Jacobian, I'm going to evaluate the Jacobian on the line y1 equals y2, we get the following matrix, right? There's a y1 out front, but then my matrix is 1, negative 1, 1, negative 1. And the spectrum of that matrix is 0. Okay, so no matter what the value of y1 were, the spectrum of this matrix is 0. Technically, then the spectrum of this whole matrix with the y1, if I take the spectrum of that matrix, I would get y1 times the set 0, but that's still the set 0. And hence, is the spectrum of my linearization greater than 0? No. Is the spectrum of my linearization less than 0? No. And hence, Hartman Grobman says it's not necessarily necessarily attracting or repelling. So that's something useful about Hartman Grobman as well, as it tells us in which cases we're not necessarily one or the other. Let's actually look at this. This is another parametric plot. Here's my line y1 equals y2. And you can see actually, so this is, I've initialized at these points. And you can see that if I start to the left, if I start on this side of the line y1 equals y2, as time moves forward, I exit that region. And if I start to the right of y1 equals y2, as time moves forward, I actually approach that region. And so it turns out I'm attracting from one side and I'm repelling from the other. So no wonder Hartman Grobman didn't say anything, because when you're attracting from one side and repelling from the other, you're going to be neither attracting nor repelling overall. And so that's why Hartman Grobman wasn't able to say anything about this. Anyway, that concludes this section. It's been a very long day. I know that. I'm sorry. I hope you find it interesting. This is some of my favorite stuff that I do. Anyway, I'll see you in class. Bye.